Hello, everybody. I hope you're all doing well. I'm back with another problem. This time we will look at a problem where we have rotating axes, where those a relative and omega cross v relative terms, those terms do not vanish in this particular problem. Okay, so here is a problem. So I have a bar AB first of all. Okay, so AB is a bar, and it is horizontal at that instant in time. Okay, and then there is a collar which you can see here. This is the collar which is appended to the end B of bar AB. Okay, so collar is appended to end B of the bar AB. Okay, so this is the information that is being written out based on the problem. Okay, so this implies that the velocity of the collar is the same as the velocity of the point B, and the acceleration of the collar is the same as the acceleration of point B. Okay, so this implies that the velocity and acceleration of the collar is the same as point B. Okay, that's one thing that we know. Then the collar moves relative to the bar CD. Okay, so the collar moves relative to the bar CD or DC, whatever you want to call it. Okay, and at the instant shown, this is the bar AB is a horizontal, and some dimensions are given to us. Okay, we are told, so given the angular velocity and angular acceleration of AB is given to us. Okay, so alpha and omega of AB, and they are told to be in the counterclockwise sense. So if I set up some kind of a coordinate frame here, okay, so let's call this as the IJK system. Okay, so this is I, this is J, and then this is the K. Okay, so omega AB, I'm told, is in the counterclockwise sense, and this is 40 K radians per second. Alpha AB is also counterclockwise. Okay, and that's 15 K radians per second square at that instant. Okay, the angle theta is given to us as 60 degrees. The distance S between the collar and the point D is given to us as 1.07 meters. And then the length L is given to us as 1.2 meters. Okay, so something that you want to keep in mind is the distance S is not a fixed distance. Okay, so this is not a fixed distance. But this length here is a fixed length. Okay, the length L, which is 1.2 meters, is a fixed length. Okay, what are the things we need to do in this problem? Okay, so find. We need to find the angular velocity and angular acceleration of bar CD. Okay, so that's the first thing. Find omega CD and alpha CD. CD or DC doesn't make a difference. Okay, the second thing is find the velocity and acceleration of the collar relative to the bar CD. Okay, so find the acceleration and velocity of the collar relative to the bar CD. Okay, and this essentially means that those terms that we hadn't been calculating earlier, those relative terms and so on, those are the ones that we are supposed to be looking at. Okay, so this is the scenario, and here is information that is given to us. So I have a bar AB which is horizontal at that instant in time. Then I have this bar CD. The bar AB has a collar attached at its end. It's been connected to the bar AB. Okay, that's something that you want to see here. The collar is pinned to the end B of the bar AB. Okay, which means that the velocity and acceleration of the collar is the same as the point B. AB is horizontal at that instant. The collar moves relative to the bar CD. Okay, so that's something that you also want to see. And bar AB is horizontal at that time instant. Okay, and the stuff that you're given is some of the geometric information at that instant in time. Okay, the angular velocity, all of these are instantaneous values that you're given. Okay, so I just want to make that clear here. Okay, so this is given at that instant in time. Okay, the angle is given to you, the angular velocity, angular acceleration, distance from between the collar and the point D. That's not a fixed length because the collar can slide relative to the bar CD. Then I have this length L, which is a fixed length because the length from A to B, which is a fixed length, is always going to be the same no matter what. Okay, and I need to find the angular acceleration of CD and the angular velocity of CD. Okay, so let me grab my picture here and let me take this down to the next page. Okay, all right, so I'm going to copy that and let's tackle this down here. Some approximations or assumptions that we're going to be making here. Okay, so I'm going to assume that the angular velocity of CD and angular acceleration of CD are in the k direction. Okay, and alpha CD is alpha CD in the k direction. Okay, so let's just mark that down here. So this is assumed. Okay, we don't know if this is correct. Hopefully we will figure it out. Okay, this is omega CD and then this is alpha CD, and here omega AB and alpha AB were given to me as counterclockwise. That's alpha AB, and I guess I need to have that on this figure here as well. So this is omega AB that was given to me, and then this was alpha AB that was given to me. Okay, all right, now what I'm going to do is I'm going to start with the easiest part of the problem. What's that? A horizontal piece, right? So I'm going to look at that horizontal bar and then I'm going to figure out, okay, hey, velocity of A is 0, velocity of D is also 0, right? And that's something that we can also see. We can I guess I can write it down, so we can also find that we see that the velocity of A is 0, acceleration of A is 0, the velocity of D is 0, and the acceleration of D is 0. This is because they are fixed points. Okay, that's something that I always typically write down. Makes life easier. Now I'm going to look at the bar AB. Okay, so bar AB. If it's a horizontal bar and if there is nothing going on relative to that bar, then I don't need to write a different coordinate frame. I can just make use of the IJK system. Okay, so I'm going to grab this guy with the collar attached to it. Okay, so I'm going to copy that. All right, and paste it. And of course, I'm going to have that's a pin that is attached at the end here. Okay, so that's going to be the point B, as you can see here. Okay, and then I have my IJK coordinate frame, which is right below here, but I'll bring it onto the next page as well. Okay, so here is my IJ and K coordinate frame with the K cut out, but don't worry, I got it. All right, velocity of A is gone. I can relate the velocity of B to the velocity of A. Okay, so here is what I do. Point A and B are on the same body. Okay, so A and B on the same body, which implies that the velocity of B slash A relative is 0, acceleration of B slash A relative is also 0. Okay, and then acceleration of A is gone, velocity of A is gone, omega AB is known to us, right? That's around 40 K, and then alpha of AB is given to us as 15K radians per second square. Okay, then I can also say the following: from point A to point B, sitting at the point A, looking at the point B. Okay, so this is A, this is B, this is R B slash A, and then this is going to be L, which is given to me as 1.2 meters. So this is 1.2 I. Okay, now I'm going to write down the velocity equation first. Velocity of B is velocity of A, omega of AB crossed with R B slash A, and then velocity of B slash A relative. Of course, this is gone. That is also gone. Okay, if I do the substitutions, then I end up having velocity of B is omega AB, which is 40k crossed with 1.2 I, and you can have your triad I, J, and then K. And K cross I is equal to J, and 12 times 4 is 48, so I get VB as 0I 48J, so many meters per second. Okay, so this is the absolute velocity of B as seen by a stationary observer. Okay, so that's something that I have found out. Then I can also use the acceleration expression. Okay, so acceleration of B is acceleration of A, then alpha AB crossed with R B slash A, omega square AB times B slash A. Then some of our relatives are gone. B slash A relative is gone. Omega AB cross V, B slash A relative is also gone. So take this term out, take that term out, take that term out. Then start substituting. Acceleration of B is alpha AB, which we were given as 15k crossed with 1.2 I, and then minus 40 square times 1.2 I. Okay, very weird, right? The number for the I direction is going to be pretty large. K cross I is J. Okay, so here I get the acceleration of B to be the following: minus 1920 I plus 18J, so many meters per second square. So this is very nice. I mean, when I looked at the problem, when I saw relative motion, I was getting a little antsy. I mean, I was getting a little scared about it. But you see, when you start off by doing something familiar, then there is nothing to worry about. Okay, so hang on to things that are familiar to you. In terms of this, here I have the bar AB. It's completely horizontal. All I'm doing is just using the equations, right? I'm not doing anything new here. Okay, so that is the story so far. Now I'm going to come to the bar where there is relative motion taking place. Okay, so let me grab that bar. So that is, well, not with that color, but that is this guy here. So I'm going to bring all of those things, and my hope is I have captured all of it. Okay, so next I come to the bar CD. Okay, that is supposed to be a straight line. All right. Okay. All right, then I need my pin here. So I guess I don't need the pin here. Or if you want, you can put a small round dot and say that, okay, hey, this was how it was connected to the previous bar. Okay, but here is the idea. This collar at B. Okay, so this is the collar, as you can see. The collar at B can slide relative to CD. Okay, so collar at B can slide relative to CD. Okay, so what this means is that if I keep the bar CD fixed, the point B is going to have a velocity relative to CD. Okay, so that is, if we keep CD fixed, the collar can slide along the length of CD. Okay, and this will also happen when CD rotates. Okay, so it's also going to start sliding. It will also slide along the length of CD as CD rotates. which tells us that the point B is not a point on the bar CD. Okay, so this tells us that B is not a point on the bar CD. Okay, because there is a relative motion between the bar and the point, even when the bar is fixed. Okay. All right, so how do I handle this particular problem? The first thing I do is I set up a coordinate frame. Okay, now it's going to be a little more cluttered, so let's keep the distances as they are, as it is. I'm going to take this figure here, I'm going to bring it down, okay, and set up a coordinate frame, and I hope this idea is clear. The collar at B can slide relative to CD, okay, that you can see. So if we keep CD fixed, the collar is going to slide along the length of CD. Even when CD is rotating, there is nothing preventing this collar from sliding along CD as CD is rotating. So this obviously tells us that B is not a point on the bar CD. Since B is not a point on the bar CD, then you can also say that velocity of B slash C relative is not 0, and acceleration of B slash C relative is not 0. That is the length S marked on the figure is not a constant length. Okay. All right, so that's great news, or I don't know, it depends on how you look at it. Okay, so here is the situation. I'm going to set up a coordinate frame now. How do I set up a coordinate frame? So I'm going to first of all set up the coordinate frame in the ijk direction. So let me take these creatures out for the time being. Okay, so here is my ijk coordinate frame. Let me have that in the red color. So that's a fixed point, so I can obviously set up an ijk coordinate frame right there. Okay, so that is I, that is J, and then that is the K direction. Okay, then I can also set up the coordinate frame that is aligned with the direction of rotation of the bar. Okay, so that's the important thing. Now I'm going to call that as an E1, E2, E3 coordinate frame. So I'm just going to draw it very long. Okay, along the line here, I'm going to draw one direction, which I'm going to call as the direction E2. Okay, and you obviously know what the direction of E1 is going to be. I'm going to choose E1 such that if I swing my arms from E1 to E2, I'm going to get E3 coming out of the page at that instant in time. Okay, so this is going to be E1, okay, such that E3 is going to be in the same direction as that, and I just want to make sure that this looks perpendicular. Okay, so and then this is going to be the direction of E3. Okay, so here E1, E2 and E3 is a body frame attached to the bar CD. Okay, this implies that the angular velocity of the frame E1, E2, E3 is the same as the angular velocity of the bar CD. Okay, because this is a body frame. Okay, this is important here. The frame IJK is a fixed frame. Okay, so IJK is a fixed frame. Okay, both of them are triads, of course. Okay, so I still have the fact that so omega of E1, E2, E3 frame is the same as omega of CD. Okay, and then if you want, you can write the omega of the IJK frame is 0. Okay, because it's a fixed frame. Okay, this is a body frame. Okay, and this is a fixed frame, and they're still triad. Okay, so I can always have that written as well. So they're triads where E1, E2, E3 are drawn this way, That's a positive sign. So this implies that E1 crossed with E2 is equal to E3. E2 crossed with E3 is equal to E1. E3 crossed with E1 is equal to E2. Okay, so this is a triad. Okay, now we are ready to handle this problem. Okay, I don't want that, but we are ready to handle the rest of the problem. All right, so I'm going to go and grab my figure from here. I'm going to copy that and I'm going to bring it down to the next page. Okay, now here is what I'm going to do. I'm going to start off with the velocity expressions. Okay, so when I do the velocity expressions, I'm going to just relate the velocity of B to the remaining velocities that I have. Okay, so velocity of B is velocity of D plus velocity of B slash D relative, which we said was not 0, right? So that's something that I had written down here. I had written B slash C. I guess I should also write B slash D. To be honest with you, I should be writing this B slash D. So let me do that very quickly. Okay, these are all B slash D. Okay, so that's B slash D. Okay, so I'm going to have that here, that is not 0 anymore, and then I'm going to have omega of the bar CD crossed with R B slash D. Okay, now how are we going to write this down? A couple of things here. First of all, velocity of point D is 0. That is known to me. That is good news to me. Okay, now VB slash D relative is going to be along the direction E2. Okay, so VB slash D relative is going to be some unknown value, and this is going to be along the E2 direction. I hope this makes sense. Why is that the case is, this is the velocity of B, so let us write this is the velocity of B relative to D as the bar CD is kept fixed. Okay, which means that this is going to be along the direction of the line CD, so that unit vector is E2 in that direction, so that's why it's going to be this way. Okay, and then omega CD, I already know RB slash D is going to be S times E2, which is 1.07 E2. Okay, so this is what I have here. All right, then I'm going to just combine everything together. So velocity of B is going to be VB slash D relative times E2, and then I'm going to have omega CD, which I do not know, but it's assumed to be in the K direction, right? So I'm assuming omega CD to be in the K direction. We don't know if this is correct or not. We will figure it out. Okay, and the K direction is the same as the E3 direction, if I want to make a note of that. So here E3 is the same as the K direction at that instant. Okay, and so this is omega CDK crossed with 1.07 E2. Okay, then I bring my triad. Okay, if you want. Never go anywhere without the triad. Okay, so in this situation, I can say that E3 is the same as the K direction. So K cross E2 is the same as E3 cross E2, which is going to be minus E1. Okay, so that's something that you can see here. So I'm going to have the following. Okay, this is in the E2 direction. Okay, which is VB slash D relative. So VB is going to be VB slash D relative E2, and then K cross E2 is going to be in the E1 direction. Okay, negative E1 direction. So minus 1.07 omega CD in the E1 direction. All right, so this is what I have here. So this is good news. Then while I'm at the bar, a CD, I'll also write the acceleration expression. Okay, so acceleration of B is acceleration of D. Then I'm going to have alpha CD cross RB slash D omega square CD times RB slash D. Then I'm going to have A B slash D relative, and then 2 times omega CD crossed with V B slash D relative. Okay, so this is what I'm going to be having. And I can bring my figure down here once again, okay, just so that we have this taken on with us every time we go somewhere. Okay, and I just want to write down a few things here. Okay, so acceleration of B slash D relative, as you can see, the acceleration, this is going to be the acceleration when the bar CD is fixed, and then I'm just taking the collar B and then sliding it along the bar CD, which means that this is going to be along the E2 direction as well. Okay, and I already know that velocity of B slash D relative is V B slash D relative in the E2 direction. Okay, we had assumed omega CD to be omega CD K. Alpha CD was alpha CD in the K direction. Okay, those are things that I already know. And then acceleration of D was equal to 0. Okay, so that's the only term I can cancel off here. RBD B slash D was going to be 1.07 in the E2, so many meters. Okay, so these are all things that I know, and I can now go ahead and write the acceleration of B as the following. So acceleration of B, let me maybe write that down here. So acceleration of B is going to be AD is 0, so alpha CD, in the K direction crossed with RB slash D 1.07 E2. Okay, and then I'm going to have a couple more. So I have my triad, which I'm always keeping on here. Then minus omega square CD scalar times 1.07 E2. Then I'm going to have A relative, which is A B slash D relative in the E2 direction. Then 2 times, look at this cross product. This is omega CD in the K direction or E3 direction crossed with V B slash D relative in the E2 direction. Okay, that's what we had there. And I'm just going to combine all these terms by looking at my triad. Okay, so if you want, you can grab your triad from here. So copy that and paste it down here. I'm going to grab my acceleration expression from here, which we had written down. Okay, and I'm going to bring it down here. Let's see, I'm going to move my triad so that I'm going to have a little more space to bring my acceleration and then get it off my chest. Okay, all right, acceleration of B is going to be the following. Now K cross E2 is going to be minus E1, so this is going to be minus 1.07 alpha CD E1. Then this is just going to be minus 1.07 omega square CD in the E2, cannot do much about that. And then I'm going to have A B slash D relative in the E2 direction, can't do much about that either. And then K cross E2 is going to be minus E1 once again, so this is going to be minus 2 times omega CD V B slash D relative in the E1 direction, and I'm going to combine them together. Okay, so that I have acceleration of B is minus 1.07 alpha CD in the E1 direction. So let's write all the even terms together. Minus 2 omega CD V B slash D relative in the E1 plus, okay, that's going to be the next set of terms, which is minus 1.07 omega square CD plus A B slash D relative. Okay, so this is what I have. I want to write this down in a much nicer way, so let me just grab this here. I'm going to copy that, making it so that it all comes up on one straight line. And if I copy that and I paste that here, well, that's not too bad. Okay, fantastic. So this is the information that I have, and so far what do we have so far? Okay, the information that we have. Okay, so from bar AB I had the following. So now I'm just combining all my information together. Okay, so from bar AB, if I go up here, I had velocity and acceleration. So I'm just gonna, well, that did not work out too well. So I'm just gonna copy that. Hang on a minute. Well, maybe I'll just do it step by step. Okay, I don't want to make you dizzy by going up and down, but I guess I have no option. Then I'm gonna go and get AB from here. So that's copied down here, and then I bring that creature down here. Okay, then I have from the bar CD. Okay, I have this velocity here. Okay, then I say, okay, from CD, I have this velocity down here. Okay, and then I have this huge guy staring at my face. Okay, so that's the information that we have. Okay, that's from bar AB and that's from bar CD. And obviously you see that, okay, if I call this as equation 1, I call this as equation 2, equation 3, and then I'm going to call this as equation 4. Okay, equation 1 is equal to equation 3. Okay, so that's exactly what I'm going to be doing. So equation 1 is equal to 3. Okay, which implies that 0I plus 48J, okay, this is going to be equal to VB slash T relative in the E2 minus 1.07 omega CD in the E1 direction. Okay, obviously I need to do a coordinate transformation. Okay, so let me bring my figure from here. Okay, so I'm going to copy that, and we can also mark omega CD in this figure if you want, since I did not mark it here. Okay, so this was omega alpha CD, I'm sorry, alpha CD. Okay, so I'm going to bring my figure here and then paste it down here. I'm going to clean it up a little bit. Okay, so I don't need any of these things at this point in time. Okay, I have E1, E2, E3, and then I have the IJ and the K coordinate frame. How do I do the transformation? There are two ways. You can either transform E1 and E2 to I and J, or I can do transformation from I and J to E1 and E2, which is easier. Okay, because I have directly relationship between VBD in the E2, and then so one unknown in E2 and one unknown in E1, right? So if I do the transformation from IJK to the E1 E2 coordinate frame, I can just equate the E1 and E2 directions and get my unknowns solved for. Okay, all right, so I'm going to transform from IJ to E1 and E2. Okay, so the first step is I pin the coordinate frames together. So I'm going to draw my E2, okay, and E1 coordinate frame this way. So this is E1, this is E2, and then I have my IJ coordinate frame drawn this way. So this is going to be the I direction, hopefully horizontal. Okay, and this is going to be the J direction. Okay, so this is J and this is I, and then I write down the information that I know. Okay, the angle theta is given to me right down here. Okay, so do the coordinate transformation. I start off by taking I and breaking it up into components along E1 and E2. So I'm going to do that first. Okay, so I'm going to take E1 and E2, copy that, and then put that down here. Okay, and then let's see, I want to bring it to a nice place here. Okay, and then I have I, which I'm going to copy and then paste it down here. Okay, all right, so if I do the coordinate transformation, here is what I end up getting. Let's see. So the angle theta is given to me here. I can take the I coordinate, I unit vector, and then drop, it has a magnitude of 1, right? So we have done this in the past, but I'm just going to do it again very quickly. Okay, so drop perpendiculars on here, and then drop perpendiculars on there. It's not a straight line. Once again, not a straight line. What's happening? All right, that's a straight line. All right, beautiful. So this is going to be sine theta, and this is going to be cosine theta, okay, which tells me that I is going to be sine theta E1 and then cosine theta E2. Okay, so that's one coordinate transformation. Then the other one I'm going to do is between J and the E1 E2 directions. That's also something that we need at some point. We may not need it right away, but it is useful to have it. Okay, so here this is the J direction. Okay, which automatically tells me that I need to take E1 and then extend it on the other side so that it happens to be this way. Okay, so this is going to be minus E1 then. And you know that this angle was given to you as theta. So if I take my figure here, right, and then I bring it down here, then I know that this angle here is also going to be equal to theta. Okay, so which means that this angle here is going to be theta. Okay, so if I do the coordinate transformation from the head of J, I drop a perpendicular down here, and then I drop a perpendicular down here. Okay, let me grab this theta and then bring it closer. Okay, fantastic. This is perpendicular, hopefully, perpendicular, hopefully. This is going to be sine theta. This is going to be cosine theta. Okay, and then you can write J is minus cosine theta E1 and then sine theta E2. Okay, so these are the coordinate transformations that we have done. And once again, these straight lines, I'm telling you, they can be very frustrating. All right, I'm sure you heard that many times before. Okay, so now I'm going to take my equation from here. Okay, I'm going to copy that and I'm going to bring that down here. Okay, so this is the equation I have. So instead of J, I'm going to substitute for E1 and E2. Okay, and then theta is 60 degrees. Okay, so here theta is 60 degrees. Okay, that's the same theta here as well. Okay, so here too, theta is 60 degrees. Okay, so do the substitution. Here is what I end up getting. So 48 times J, which is minus cosine 60 E1 and then sine 60 E2. This is minus 1.07 omega CD E1, and then this is going to be V B slash D relative E2. Okay, so if I look at the terms containing E1, terms containing E2. Okay, terms containing E1 minus 48 cosine 60, that's minus 1.07 omega CD, which tells me that omega CD can be solved for. It's a positive value for me. Okay, and omega CD is 22.4 radians per second. Okay, not square. All right, so I found out one of them. Then I have the other term, the E2 term. You see, this has become so easy, right? 48 sine 60 is equal to VB slash D relative, which implies that VB slash D relative is 48 times sine 60, which is approximately 41.6 meters per second. All right, fantastic stuff. So we're almost there. And these are all positive, so this tells me that, okay, hey, since we obtained positive quantities, this implies that omega CD is actually 22.4 K radians per second, and VB slash D relative is going to be 41.6 in the E2 meters per second. Okay, so this is what we have, and This is the velocity of the collar at B relative to CD. Okay, so we're done with one part, and then we have the last part, and then we can call it a day after that. All right, so I'm going to bring the acceleration expressions which we have here. So I'm going to equate equation 2 to equation 4, as you can very well see. Okay, so I'm going to first bring equation 2. I'm going to try and copy that. Okay, so the acceleration expressions I'm going to equate, so let me write this down here. Equate equation 2 to equation 4. Okay, that is my next step for the acceleration analysis. Now this is equal to this big creature which we had written down here. Okay, fairly giant expression, which I'll try to see if I can fit in on a single straight line here. Okay, I need to do some adjustments. Let me do that here. Okay, and let's see. I should be able to do it, I think. Almost. Let me maybe adjust some things here. Okay, apologies for doing this, but I want to get them all on the same line. Okay, so that it's very obvious to see as to what we are trying to do here. Okay, this is fantastic. Okay, beautiful. So what am I going to do now? I also have my coordinate transformations, right? So I'm going to grab those two creatures as well. Okay, so this is my coordinate transformation from some time back. This is what I have, and then I also have calculated. Okay, so omega CD, which we found out to be 22.4 radians per second, and then VB/D relative, which we found out to be 41.6 meters per second. Okay, so then all I have to do is do the substitutions. Okay, so minus 1920 times I, which is sine 60 E1 cosine 60 E2, plus 18J, which is minus cosine 60 E1 sine 60 E2. This is what I have on the left hand side. This has to be equal to all these big guns put together on the right hand side. Okay, so I need to bring them down here. Okay, beautiful. Then I do the same thing as before. Take the E1 terms, take the E2 terms. What are the terms containing E1? Minus 1920 sine 60 minus 18 cosine 60, right? And then terms containing E1 here are going to be minus 1.07 alpha CD minus 2 times omega CD, which I'm going to substitute as 22.4 times VB/D relative, which is 41.6. Okay, so that's one thing that I have done here. Okay, then I do the same thing on the other things on the E2 side. So that's going to be minus 1920 cosine 60 plus 18 sine 60. This is equal to minus 1.07 times 22.4 square, okay, plus AB/D relative. Okay, so that is exactly what we have done so far. Okay, then if I start doing the solution for all of these things, let's see how it works out. Okay, so alpha CD I will end up getting as the following. Okay, so let's see, I'm going to look at this equation. Let me call that as equation 5 and then equation 6. Okay, so from equation 5 I have the following. So minus 1.07 alpha CD is minus 1920 sine 60, 18 cosine 60, and it's going to be plus 2 times 22.4 times 41.6. Okay, and alpha CD, if I put a positive sign, it's going to be positive, and then this is going to be a negative sign. Okay, and I will end up having this quantity, the negative quantity, overshadowing the positive quantity. So alpha CD will end up being negative for me. So minus 407.5 radians per second square, which implies that alpha CD is minus 407.5 K radians per second square, or minus 407.5 E3 radians per second square. Okay, so that's the same. Then I can take stuff from the equation 6. So this is from equation 5 here. Then I take equation 6, which I have here, this big guy. Okay, just copy that and bring that down here. Okay, so from there, what do I see? A, B slash D relative. Okay, so this is 18 sine 60. Okay, minus 1920 cosine 60, and then it's going to be plus 1.07 times 22.4 square. Okay, and this will I apologize, this alpha CD is I just switched off the the answers for each of them, so that's not nice of me. This was supposed to be a different answer. I just caught the jitters here. Okay, this is going to be minus 180. I apologize. Okay, I'm not sure why that came out again. Okay, so this is minus 180. Okay, so this is minus 180K or 180 E3. And in this situation, okay, if I do A, B slash D relative, and this is now going to come out to be positive for me. So A, B slash D relative will end up being the value that I had written earlier, which was 407.5 meters per second square. Okay, and this is the acceleration of B, the collar, relative to the bar CD. All right, so that's a pretty heavy problem, right? I mean, I hope you agree with me on that. Okay, let me very briefly go back and then look at the problem again. Okay, here is the situation. It looks like a simple problem, but that's not the case. I have two bars which are coupled together by means of a collar. Okay, bar AB is horizontal to begin with. Bar CD is at an angle. Both of them are rotating. At that instant in time, the bar AB is horizontal. The collar B is attached to the bar AB, which means that the collar B can slide relative to the bar CD. I need to find the angular velocity and angular acceleration of CD, and I need to find the relative velocity and acceleration of the collar B with respect to the bar CD. Okay, my strategy is I look at the bar AB first. The collar is attached to the point B, so B collar is a part of the bar AB. Okay, so in this situation, and there's a pin there, okay, so that the collar can rotate about that pin, but the collar is kind of very small in dimension, so we don't treat that as a rigid body as such. So B is a part of the body AB. I just make use of my regular velocity and acceleration equations, and I find out the acceleration and velocity of the point B, okay, which is the same as the collar B. Okay, then I go to the bar CD. I see that, okay, hey, here the collar can move relative to the bar CD. So the point B is not a point on the bar CD, okay, which means that this VB slash D relative and AB slash D relative is not necessarily zero. They may end up being zero because of mathematical coincidence, but it is not necessary that they do be zero. But at least to begin with, we will not say that they are zero, okay, because obviously B is not a point on the bar CD. Then I start up a body frame of reference E1, E2, E3 attached to the bar CD. This body frame has the same angular velocity as the bar CD, which is omega CD. IJK is a fixed coordinate frame. Okay, it does not have any angular velocity. Then I make use of my velocity equations, regular velocity equations, relative velocity along the direction E2. And E1 and E2 are chosen such that if I take the fingers of my right hand, align it with E1, align the fingers of my right hand with E1, bring them towards E2. The direction of my thumb coming out of the page is the direction of E3, which is coincident with K. Okay, so that's why I chose E1, E2 to be this way. There is no hard and fast rule. You can choose E1 to be along the line CD, E2 can be, to the left of E1, and then E3 can come out of the page. That's also fine. Okay, then I obtain VB, and likewise I obtain AB as well in terms of some unknown quantities. And then I already say, okay, hey, From bar AB, I had these expressions. From bar CD, I have these expressions. All I have to do is just equate them all together. Okay, but before I do that, I have to do a coordinate transformation. Okay, am I going to go from E1, E2 to I and J, or vice versa? I have to do from I and J to E1 and E2 because that is easier for me. But either way is fine. Okay, if you want to make your problem a little longer, you can use the coordinate transformation from E1 and E2 and go on to I and J. But for me, this is shorter because I have two unknowns, one in the E1, one in the E2. Then I just transform J into the E1, E2. I'm equaling the E1 and E2 terms on both sides. That's exactly what I'm doing here. Coordinate transformation is done. Equate the E1 and E2 terms, omega CD, VBCD, VBD relative is obtained. We obtain positive values, so this is what we have. And likewise, I do the same with the acceleration expressions as well. These are slightly unwieldy, but they're still not too bad. Okay, equate the E1 and E2 terms, you'll be able to obtain alpha CD and A B slash D relative. The acceleration of B relative to the bar CD. All right, so that's a good problem. We will solve a few more of these types in the coming weeks. All right, thank you very much and take care of yourselves. Bye-bye.